everybody. Now we really want to decouple the system, and therefore we assume the system that we've introduced in the last video. So in this example, we say this is our plant site, this is our real world example, this is the system. The system behavior, maybe the reactor or a distillation column or whatever. This is our system. Then we have our control blocks in here. And what there's two are new blocks, and those are this GD1 and GD2 blocks. What are these? These are our decouplers that we introduced. So those are on one side two controllers and two decouplers. So, and what you would implement in the real world is one plant, so one plant side, one system behavior, and on the other side, one big controller. And this controller has those four parts. They have the direct control for our output variables, so those GCs. And on the other hand, the decouplers are implemented as well. And in this video, we want to actually design these decouplers in that way that the interaction between those control loops is excluded perfectly. Now we actually need to close those loops. So in that way. So now they are closed. And yeah, let's design those GDs. What do we do? In the first place, we want to describe our UEs as follows. We say U1, what is it? It equals V1 on one side plus GD1 times V2 times V2. Okay, this is one thing we know, and on the other hand, we know it from for U2. And for U2, it's actually V2 plus GD2 times V1. So actually just the other way around. So we just shifted some numbers. Now we can perform this for our output variables VE. So Y1 equals, what equals it? It equals G11. G11 times what? Times U1 plus G12 times this part, and this part is U2. And the same applies for Y2. It's G22 times U2 plus G21 times U1. That is what we know. And now we want to introduce this and make it a bit more difficult. So now we write one step for V1. So when we put in our U's, we will get it equals G11 plus G12 times GD2 and everything times V1. plus G12 plus GD1 times G11 times V2. So that's it for the first place. And for the second equation, we can write Y2 is G21 plus G22 times GD2 times V1 plus G22 plus G21 times GD2 and everything multiplied by V2. And what we now want to set is the following. We want to eliminate the effect of Y2 and on Y1. So what we want to get rid of is Y2 has now an influence on Y1, and we would like to cross this out. And the same applies for Y1 on U2, and we want to cross this out as well. How do we do this? Well, we can now write that for V1, the influence of V2 should be 0. And this means that we can say, G11 times GD1 plus G12 equals 0. And it can be clearly seen when we separate GD1, one of our decouplers, that we get GD1 equals minus G12 over G11. And this is our first decoupler that we've just calculated. And the same applies for the second decoupler. We write down G21 plus G22 times G2D2 equals 0. And for our decoupler, this means G22 equals minus G21 over G22. And this is our second decoupler. Great, now we have them. Now we can use them when we have the transfer functions. Now we can use them, put them in our big controller that we, they can be implemented as one big controller. So this is one module, if you like so. Okay, put them in. And what we now get is a dynamic decoupling system. So the system is dynamically decoupled, and we can use such an approach in around about 90% of all cases. And yeah, that's a quite good decoupling technique for separating this interaction. All right, thanks for watching and see you in the next lecture.